Python meeting. Today we have Sebastián Ramírez, and he's going to show us how to use Numpy and Pandas in a very professional way. So thank you everyone for coming and everyone who may be watching online. So you have 20
Okay,
minutes.
sure, thanks. So this is not so much as a professional guide, but more of a bag of tricks that may be useful to you to like solve some problems using NumPy and Pandas that you may or may not know about, but getting to know some functions that are new and some ideas might help to reduce your length in code and its efficiency. So for starters, I just have some, yeah. Yeah, so I have some basic spectra from DESI, some table, for example, and just some spectrums, and a basic plotter function that I will use in many cell codes. So this is basically how some of the spectra look. It's nothing new. It's some galaxies with some emission and lines and some continuum. And this will be what we will be working on. So, as a first step, something that you might want to do for a spectrum of this type is to subtract the continuum. So what you would typically do is maybe iterate over every single spectrum and calculate a polyfit and get that continuum to get some kind of approximation. And you do it probably like a for loop that goes through every one of the spectrums. But it's a lot more simple actually. You can actually, for example, do a polyfit over every single spectra. You take the degree, and this will generate a single array that has a shape of the number of degrees in your polynomial and 500, which corresponds to the number of spectrums that I have. So you don't have to iterate. You can just take a single function and apply it, and then you use polyval to get the single continuum of every single spectrum. You divide it, and then you get the basic continuum subtracted from the spectrums. This is a lot neater than doing a for loop that may take some time, and it's faster. So, and that's the first thing, like polyfit for multi-shapes of arrays. Then you might want to like some kind of redshift correction. So, for example, in my table that corresponds to the spectrums, um, I have the redshift of every single one. As you can see, it's 500 rows, one to one. So I just transform it to a NumPy array, getting the redshifts. But you may notice that the wavelengths that we have a shape of 7,000, like 7,000 different data points of wavelengths, while you have just 500 redshifts, which makes sense, but it's not desired. And if you take, for example, our wavelength and divide it over C, you will get an error. You will get that the shapes couldn't be broadcasted. So to fix that, you can do what's called broadcasting in NumPy. Um, and you can basically add extra dimensions into your arrays. So for example, if you take C, before it had a shape of 500, but if you do the broadcasting, it should add an additional shape. So you have 501. And with this additional one, this can be broadcasted into the 7,000 shape. So you can get now this new wavelength at rest frame, which has a new shape of 500, 7,000. So now it's a two-dimensional array, which you can use to plot every single wavelength. But if you also want to combine them again into a single wavelength array, you might like want to have some fixed structure for your wavelengths instead of having multiple data points. You can do a simple interpolation for each one. So you take a reference frame of wavelengths, you interpolate the data from the rest ones that we've got, and you get a new wavelength reference, which has now a shape of 500 times 7,000. And the wavelength has a shape of just 7,000. So you got from different wavelengths that were redshifted, you can reduce them into a single one that is on the rest frame. And this maybe is weird, but if you look at the spectra, this is what we have before. So we had like different wavelengths that were redshifted a bit. This is a global, I mean, a galaxy cluster. So they are pretty similar. But if you correct for the redshifts, now you have these straight lines signaling like common emission lines. And I highlighted these ones for something that will come after. So what's important, the takeaway, is that you can combine different shapes if you do what's called broadcasting, which is adding additional dimensions into your arrays. Then something that you may also want to do is some kind of smoothing over your spectrum. There's a neat function that divides your array into different windows. For example, this one, a sliding window view, what we'll do is take your whole array and we'll move it a bit to the right for multiple windows. For example, in this case, we set 100 windows. So we will have 100 different shifts into your spectrum, and it will look something like this. So each you have 100 of these shifted spectrums. And what's cool about this is that if you take a single slice of all these spectrums, you may notice that we have some to the left and some to the right. But if we take them in on this single line, we will take an average of the circumvent of the close points, and that will allow us to reduce those 100 points into a single mean. And if we take that mean, we will get a smooth spectra. So that's cool about sliding windows. You could also do like some algorithm that needs to take a single shape. For example, if you have a machine learning input that may need a shape of, I don't know, 100 data points, you can take multiple windows of your spectrum and apply that algorithm into each individual window instead of like trying to loop over something. So it's really useful, this particular function. This is pending. So yeah, I will skip over that. And lastly, for spectros, I also want to show a bit more of broadcasting. So for example, if we want to take the equivalent width of these previous emission lines that we saw, that were here, we might want to do something like 1 minus the flux ratios times the lambda differential, which is like a good formula for the equivalent width. And we would, for a single emission line, we would do something like this. So we take the spectrum, we mask a region that is defined by these wavelengths in that region, and we multiply that by the differential, which by the way is measured with the gradient function. But if you check that, it's just the same number repeated over and over. We can take the sum of the equivalent widths, approximating the integral into a sum, and then we get the equivalent width of every single spectrum that we saw. And this is the histogram. This is what the equivalent width of those lines that we saw before. Some are negative. Probably they are not there. but it corresponds to this equivalent width, basically. And that's something that you probably know of, like this type of masking and taking sums and everything. But what's cool if you want to look at more than a single line, you can take an array that defines multiple lines. So for example, if we want to look at the 7000 and these 7500 lines, um, we can define our masks with the same idea. And we do the same kind of broadcasting that we had before. So we add new dimensions into our spectrum and our mask. And instead of before that we had a shape of, sorry, 500 spectrums times 7,000 wavelengths. Now that we have two lines, we actually can do a spectrum that, sorry, a flux array that goes from 500 times two lines times the window width and transforms that into the equivalent width of each spectrum. So this is the same as before, basically. It's just taking the integral, but you can do that over multiple lines in just one go if you add dimensions with broadcasting. And this is the correlation that it's probably wrong. I don't think that the lines are quite well defined, but the idea is correct. So yeah.
Oh, I'm assuming it's faster to add dimensions and do instead of doing like a four and go.
Yeah, most of the times it's faster to.
Is it always the case? So what happens if you have like, I don't know, 50 lines?
Numpy is faster, basically,
Yeah.
always.
Faster.
Oh, I mean, if you have 50 lines, you will have one dimension
Yes.
additionally. It's just a 50. So yeah, I didn't bring a comparison with like typical for loops, but it's a lot slower.
So that's it. We can use Daniela's Python
Yeah.
to compare the lines.
Thanks.
So yeah, that's like is a big part of what I wanted to show, like NumPy functions. Broadcasting is like one of the most essentials, like advanced topics that may appear in NumPy, and there is a lot more to check regarding also linear algebra and all that stuff that we typically don't use.
It's just, I think it's very cool. I didn't know you could like do a mask with different like arrays. But then when you apply the masks to the fluxes, does it have like two different like extensions? Like the first one is the first mask and the second one is the second. It makes the mask for both lines.
So you have a mask that is that has this shape basically. So it's it's both lines. If I added a third, like I don't know, 5,000, it adds an extra point in this dimension. Okay, then, and I also wanted to talk a bit about pandas. So this will be a lot faster and it's easier to look at also. So first, I have some more DAISY data. It's just a count search below 0.4 redshift. And so the first thing is that if you want to look at your data like really easily, you may just want to take the data frame, put a .ist on that, and it just plots every single column in your data frame. So it's a lot faster than like going through every single plot and column and trying to do things. Also, another thing that is really cool and simplifies life a lot is Seaborn. So you may know it, but you can do scatter plots that are compatible with Matplotlib, but that are also compatible with the pandas. So if you plug your data frame into Seaborn, it knows how to read it. So you can pass like the name of your columns without having to worry about like doing df open I don't know, the corchetes, and doing all that stuff. You can like do a more readable code with Seaborn. So, well, this is the corrected color versus redshift, like a K correction. And also with Seaborn and NumPy and Pandas, you can define, for example, a condition. So if I want to make a condition for the red sequence, the green valley, and the blue cloud, just with this basic criteria of color versus redshift, I can define my color above 0.55 like the red sequence, and below 0.45 like the the blue cloud. And everything else is the green valley. So this is the condition, and this is the choices that have those names. So you have the red sequence, the blue cloud with these conditions. And if you do numpy.select, it will basically take each object in your yeah, in your data frame, thank you, and apply that. So you get this. You get a new column that has like the classifications that you define with your conditions. And with Seaborn, you can also do the hue, which is basically color. You put this new column and it will plot it for you. Um, s- uh, so something that is also useful is aggregation, which basically pandas know how to handle this. So you can do groups. For example, if you do just a single group by, it doesn't work. Okay, I don't know why. But you can do groups by survey and spec type. In this case, I just have one single survey, which is main, but I have different spec types in my data frame. So I have quasars, galaxies, and stars. And I can tell pandas to group them by different things or to take different analysis. So for example, for the IDs, it just counts them if you put size. And so you have 1700 quasars, you have like 200,000 galaxies and 12 stars. This is what size means. But you can also take like, for example, the mean of some column, it will give you the statistic of that column. So, for example, if you put the redshift and the mean, it will calculate the mean of that particular group. So quasars have a mean of the redshift that it's a lot higher than stars, surprisingly. And the same with median, etc. So it's really useful to have like statistics of your data. And yeah, you can do also something similar with lambda functions, which I may not have the time. So I'm going to go really quickly. You can also do like SQL types queries. For example, spec type equals galaxy and blah, blah, blah. Instead of doing masks, you can do a single strings to query your data. You can do that with functions too, which may calculate different things in your data. And you can also use the rank function, which basically sets up a rank. So it basically sorts a column, in this case, the magnitude, and it assigns a rank. So the rank means that the brightest galaxy will have the rank 1, the second brightest will have rank 2, and so on. So it looks like this, like the brightest galaxy is in here. This is just what we saw before, same things. Some merge and concatenation, which you probably know how to do. So I took like a morphology categorization from DESI and made the same plots with Seaborn here. And as a bonus from everything that we have here, I also wanted to show that you can plug pandas tables into AstroPy tables, as you may know. And if you do like showing browser or showing notebook with JS Viewer, and it opens, you may take interactive tables that you can like sort and search for. I don't know, you want to search an ID. Yeah.
So like Excel and Pandas and Numpy. Oh, that's so cool.
So yeah, that's basically it. Thank you for listening.
Okay, so any questions? I have a lot of questions. So, anyone? No? Okay, so I have many questions. First, I'm very impressed by pandas because I usually just open stuff in pandas
Yeah.
and then I use it like a table, like whatever I do like the most. My question is when you do like the sort by, where you like you have like the mean and the count, does it have like already like certain parameters that you can group by? Like for example, if I want to do something else, it's what is this like size mean and what else can I do?
Honestly, I don't know. We could check right now, but probably like I don't know, skewness mode.
Yeah.
Let me see. It's actually a good question. Pandas aggregation. Um, my God. Okay, maybe I have to come back on that. Dot ag. Yeah, I can tell you later. I'm not sure which ones are available. I think so. Yeah.
That part the query that was oh my god, like is that like the query inside your data frame?
Yeah, actually it's not SQL. So it follows like different. Yeah, it works like a mask basically. You can do or and, but if you take like the SQL notation and you put like this, it breaks down. So you have to check for the notation, but it works.
We have the same notation of mass, like if you put the and or oh.
Ah, right. Yeah, because that's what I was thinking. Because when you do the mask, you have to put like the parentheses
Yeah.
and the and then the other parentheses, and sometimes like it breaks. But this seems easier, I think.
More readable too.
And it's faster, I think. The query.
Oh,
Yeah, it works in C basically. Yeah.
I use it a lot to with the tables of the simulation. I basically do tables, I mean data frames and do queries because it's much faster than doing math.
Yeah.
It's very, very fast and nice to like easy to work on. I love queries so much. Yeah.
okay, so amazing. So thank you, Seba, again.
Oh,
I think it was actually very good and professional. So and thank you everyone who might be watching. And always a reminder that if you're watching this on YouTube, we might probably be doing this for a long time. So subscribe and like. And what else? I'm missing and comment. Leave a comment. And see you next
like
week.
button.
This is a shameless promo because I am presenting next week. So thank you and bye.